Shahnawaz. This is the 5th lecture on metric spaces. In last lecture we have seen that there exists metric spaces where a Cauchy-Schwickens will not converge top point in that space. For example, we have seen that the metric space CAB, space of all continuous functions on the interval AB with respect to the metric d of fg equal to integral a to b absolute value of fx minus gx dx, where this f and g, they are continuous functions over the interval AB. So we have seen that this metric space will not converge in CAB. Thus, the metric spaces in which Cauchy-Schwickens are guaranteed to converge are special, and we need a name for them. So we have a definition. We say a metric space xt is said to be complete. Metric space is said to be complete metric space if every Cauchy-Schwickens in X converges. If every Cauchy-Schwickens in X is convergent. Now there are certain examples of metric spaces which are convergent, and also certain examples of metric spaces which are not complete metric spaces. For example, let us make it as a proposition. So if we consider the metric space Rn, the metric space X is equal to Rn with the metric given by of xy equal to sigma Rn from 1 to n mod of xi minus yi to the power p over the power 1 over p, where this p is bigger or equal to 1. So, and this x and y, they are n topology Rn, where x is equal to x1 through xn and y is equal to y1 through yn. Ru r to the power n. So this is a complete metric space. So generalize this proposition. So we'll consider a sequence in Rn, and we take it to be the Cauchy sequence, and we'll prove that Cauchy sequence is convergent in Rn. So let xn, where this n is bigger or equal to 1, and this xn is an n tuple in Rn, i.e. it is given to be equal to x1 and x2 and so on, xn n. So let this denote a Cauchy sequence. Xt. Note that here in this sequence, each term of this sequence is an n tuple in Rn, where each component of that n tuple is a real number. So if this is a Cauchy sequence, therefore dp of xn comma xn prime, this goes to 0 as n prime, this goes to infinity, i.e. the distance between arbitrary two terms, arbitrary large two terms in the sequence tends to 0. So if this is true, that means for any epsilon positive there is an integer n naught, i.e. then for any there exists an integer say n naught epsilon, i.e. this integer n naught, this depends on epsilon, such that dp of xn prime, this is less than epsilon, but this n and n prime surpasses this n naught. So this is true for all n and n prime bigger or equal to n naught. So by definition, this implies say k1 is from 1 to n, absolute value of xkn minus xkn prime. So this whole to the power 1 over p, this is less than epsilon for all n and n prime bigger or equal to n naught epsilon. So now if this whole sum is less than epsilon, now in this sum each term being non-negative, this implies each individual term is less than epsilon. Hence xkn minus xkn prime is less than epsilon. Because whole sum is less than epsilon, this implies every individual term will be less than epsilon. So this is true for all n m prime bigger or equal to n naught epsilon, and all k running from 1 to n, because this is true for each individual term. Now upon fixing k, it follows that xkm, like this, m is bigger or equal to 1, converges to limit say xk. So this converges to xk, i.e. that is limit m goes to infinity xkm. This is nothing but xk. Now if we let x to be equal to the m tuple x1 x2 through xn in r power n, and m, if we take m to be bigger or equal to n naught epsilon, it follows from here. So if we keep this inequality over here, let us keep it equation inequality 1. So it follows from 1 that sigma k goes from 1 to m, xkm minus xkm prime, xkm minus xkm prime to the power p. It is less than epsilon over p for all m prime bigger or equal to m naught. Now if we let this m prime to tend infinity, then this xkm prime, this converges to x. Letting m prime tend to infinity, so keep it second here, letting m prime tending to infinity in second, we have, so this xkm prime, this will converge to xk, so we have k goes from 1 to m xkm minus, so this will tend to xk over p. This will be less or equal to epsilon over p for all m bigger or equal to m naught. So this is true for all m bigger than m naught. So this implies that this sequence x power m, this implies that this sequence x power m converges to x. This further implies x and this sequence converges to x, because in the sequence is defined to be like this. So here xn is like this, x1 and x2 and xn. If we let n tend to infinity, so this x1 and this converges to x, x2 and this converges to x. So let us write it over here. Let us make a side note here. So we have xn equal to, so this is some term in the sequence. So this term is given to be equal to x1 and x2 and so on, xn, xnn, as I have already mentioned that each term in the sequence is an n tuple in Rn. So if I let n tend to infinity, so if n goes to infinity, so this x1, this goes to x1 as n goes to infinity, this goes to x2, so this goes to xn. So this is same as x. So if n goes to infinity, x power n equals to x. Now this x is in Rn, that means this Cauchy sequence which we had chosen earlier, this converges to some point in the space. Therefore Rn is complete with respect to the metric as given above. So let us do one more example. Let us consider the sequence space LP, the pth summable sequences. So proposition so the metric space xt where this x is LP, i.e. where x denotes the space of all sequences, the space of all sequences of real numbers for which sigma k running from 1 to infinity xk p whole power 1 over p. This is less than epsilon. Sorry, this is finite quantity. This is less than infinity, and this p is bigger or equal to 1. And d is the metric. D is the metric given by so dp of xy, this is called sigma k runs from 1 to infinity xk minus yk from whole p whole by. Now this x and y, they are the infinite sequences in x. Now this sequence with respect to this metric is a complete metric space. Is a complete metric space. As I have mentioned earlier, this sequence is also called the LP space. So that is what we do, we take a Cauchy sequence in this space and we prove that it converges to a point in this space. So let us consider a sequence. Let xn, where this n is bigger or equal to 1. So let us take this as a sequence. Now note that each term of this sequence is itself a sequence, i.e. if we take the term xn, this xn is itself a sequence, is going to be equal to x1n, x2n, and so on. So this is an infinite sequence where this xn is some term in this sequence. This be a Cauchy sequence. In xt. So if this is Cauchy sequence, that means distance between two terms after some stage at 10 to 0. Therefore, dp of xn and xn, where these are two terms of the sequences, so their distance, it goes to 0 as n goes to infinity. This implies that if we choose any epsilon positive, for that epsilon positive there exists an integer, say n0, for which this distance over here is less than epsilon. So then for given any epsilon positive, there exists an integer n0, which depends on epsilon, such that dp of xn. So after some stage, the distance between these two terms of the sequence, it becomes less than epsilon. So this is true only when n and m surpasses n0. Or by definition of this metric, when sigma k goes from 1 to infinity, xkn, this thing is less than epsilon whenever n and m surpasses n0. Now again, this is a sum over here. This infinite sum is a sum of non-negative terms. So if this whole sum is less than epsilon, this further implies that every individual term will be less than epsilon, because each individual term is non-negative. This implies that xkn minus xkn, this is less than epsilon for all n0 epsilon. the sequence xkn, where this n is bigger or equal to 1, is a Cauchy sequence. That is for each fixed k, the sequence xkn, where this n is bigger or equal to 1, is a Cauchy sequence. Cauchy sequence of real numbers. If this is a Cauchy sequence, that means it must have a limit, because every Cauchy sequence of real numbers is convergent. Therefore, limit n goes to infinity xkn, this is the finite limit. Suppose this is equal to xk. Now let us consider a sequence. Let x equal x1 x4 be a sequence, be a sequence of real numbers. Now this x is x, and now what we are gonna do, we will prove that for the sequence over here, this converges to this x. This is what we have to prove. So let us mark this inequality as inequality 1. From 1 we have sigma k ranges from 1 to n. So we take a finite number here, xkn minus xkn to the power p is less than epsilon over p. So this is obviously true, because if this infinite sum is less than epsilon, so sum of first capital N terms will also be less than epsilon. So let us mark this as inequality 2. So if this is true, so this is true for any positive integer n, provided this n and m they surpass n naught, provided n and m is bigger or equal to n naught epsilon. Now if we let this m tend to infinity, we have let n goes to infinity, letting in second, we have sigma k goes from 1 to capital N xkn minus, now here we have taken the limit of this sequence to be xk. So if we let n tend to infinity, this sequence over here, this will tend to xk. This is less than epsilon power p. So this is true for any positive integer n, for any positive integer n, and in this so n bigger or equal to n naught epsilon. So if we consider this sequence, so the sequence so the sequence sigma k goes from 1 to n xk n minus xk power p, so p to the power p. So this is sequence. So this sequence is monotonically increasing because each term in the sum is non-negative. So if we put n first n equal to 1 and then n equal to 2, the preceding sum will be less or equal to the succeeding sum. So this is a monotonically increasing sequence. Is that monotonically increasing sequence which is bounded above, which is bounded above. So as we have seen in this sequence for given n capital N, this is bound above by epsilon power p. So if we have a monotonically increasing sequence which is bound above, then that sequence must converge to this limit supremum. Therefore this sequence has a finite limit. Therefore this sequence converges to this limit supremum. Now this is the non-negative sequence, so that supremum will be equal to i.e. at a finite limit which is equal to sigma k goes from 1 to infinity xkn minus xk to the power p, which is less than or equal to epsilon positive, which is less than or equal to epsilon to the power p. So hence what we obtain is that sigma k goes from 1 to infinity xk n minus xk to the power p whole power 1 over p. So this would be less than epsilon for our n bigger equal n naught epsilon. So now observe that this sigma k runs from 1 to infinity xk power p whole power 1 over p. This will be equal sigma k power 1 over k power k from 1 to infinity xk power n minus xk plus xk the power p whole power 1 over p. Now if we use unit cos k inequality here, if we take this as first term and this second term, so this will be less or equal to, using unit cos k inequality, this will be less or equal k from 1 to infinity xk n minus xk power p whole power over b plus sigma k equals to 1 to infinity xk m power b equals to infinity. Minkowski is inequality. Now this sum is over here, this is less than epsilon and this is also finite. So this means that this means that this x to the power n it goes to x in x. So the reason is this inequality here. So if we keep this as inequality, so this is true in x